Okay, so we've been talking about cell potentials, we've talked about free energy, we've talked about equilibrium constants. These three quantities are all related to each other. For a spontaneous reaction, delta G is negative, the cell potential is positive, and the equilibrium constant would be greater than 1. In a non-spontaneous reaction, the opposite is true. Delta G is positive, cell potential is negative, and K is less than 1. So we have these three quantities, and they are related to each other. We're going to look at how they are related. Okay, so potential difference is the potential energy difference per unit charge, and that is the maximum work. So we can say that the potential is the potential energy difference per unit of charge, and this is equal to the maximum work. This is charge Q. So E then equals work divided by Q. So we could take this and rearrange it, and we find out that the maximum work is equal to negative Q times E cell. Anybody else have a question about that? What's funny about that? Where'd the negative come from? There's no negative up here. Am I missing something?
Yeah, why is it?
Off the top of my head, I do not know.
How many times or do you get it on the first night? Subtract.
My guess is to make the sign conventions correct. So work can be positive or negative. Am I doing the work? Is the system doing the work? That's negative. Is work being done on the system? That's positive. Q can be positive or negative depending on whether charge is going in or out. So that's my best guess. I actually looked at these slides today. Did it help? No, it didn't. So I'll go back to not looking at them. So the charge that flows in a chemical reaction, so it's, like how many electrons are flowing, right? We quantify that using something called Faraday's constant. This is the charge of 1 mole of electrons measured in coulombs. So 1 mole of electrons has a charge of 96,485 coulombs. Kind of an odd number, huh? In more ways than one. So then the total charge is this many coulombs per mole times the moles of electrons that are being transferred. So on Monday, when we were adding equations and adding potentials, we didn't multiply the potentials by a coefficient, right? We just added them. If the equations were doubled, we said, we'll take care of that later. This is where the later comes in. This is where the number of moles of electrons becomes important. So we can substitute, so the maximum work equals negative Q times the cell potential. We just said that Q was N times F. And then the standard free energy for a chemical reaction is the maximum amount of work that can be done, right? It's the maximum amount of work the maximum amount of energy free to do work. So for work, we can substitute in delta G. So here's one of our equations. Delta G is equal to negative NF times the standard cell potential. N is the moles of electrons transferred in the balanced equation. F is Faraday's constant, and this is the standard cell potential. Again, Faraday's constant is this guy right here. You don't need to memorize that. Let me double check. Yep, that's given on your useful information for exams. So use tabulated electrode potentials to calculate delta G for this reaction. Is it spontaneous? So the equation we're going to use is this one, delta G equals negative NFE. So we need the cell potential for this chemical reaction. And this is what we learned how to do on Monday. So I've got an oxidation and a reduction here. Sometimes you can look at these and just kind of pick them out. Other times you really need to write two half reactions. Let's write two half reactions here. So 2 sodiums is going to become 2 sodium ions. And then there's going to be some electrons involved, right? We can figure out the number because the charge on each side has to be equal. 0 on the left, positive 2 on the right, so 2 electrons. And then the rest of it, this is our oxidation. Oxidation is loss of electrons. This one then has to be our reduction. And if we look at the charges, 0 on the left, minus 2 on the right, we can see we need to put 2 electrons over there. Any questions about that? This is like, the half reaction method, but we're starting with the balanced equation and we're working backwards a little bit. The number of moles of electrons here is our N. And so we do need to be able to figure out what that is. And then we have 2 half reactions, and we need to look up their potentials. And I'm going to do a little rearranging here. Because I forgot to leave room to write the cell potentials. Okay, so we need to figure out the electrode potentials for here. So we look in our standard half reactions, and we're going to find these guys. So we've got sodium. This has sodium plus on one side and sodium 0 on the other, and that matches what I've got up here. Then I need one where I have water on one side, hydrogen and hydroxide on the other side. And that one is right here. Okay? I split the reaction into 2 half reactions. I located them in the table of standard electrode potentials. So these are the numbers we're going to use. So the one for the water is negative 0.83. And the one for the sodium is negative 2.71. Now, if you want to do cathode minus anode, you can do that. What I prefer to do is look at these and say, which one matches exactly how it's written over here? This one, right? Everything's on the same side. So that number is going to stay the same. This one is backwards. You see that? Instead of sodium ion on the left, we have sodium ions on the right. So if the equation is written backwards, we change the sign. Multiply by negative 1. So that becomes a positive. Okay? And then we add these together. So 2.71 plus negative 0.83 is 1.88 volts. And that's our standard cell potential. Any questions? We learned how to do that on Tuesday. No, Monday. I don't know what day it is. And that's an important skill to be able to do. So that's E-cell. And then when we look at this, at the half reactions, we're looking at the number of moles of electrons in this one, not in here. So here, that one has 2, and this one only has 1. But what they did is you multiplied this by 2, right? And so now this also has 2 electrons. So the number of electrons here is going to be the same for the oxidation and the reaction. So N is 2, and F, see if I remember, 96,800, 485. Such a weird number. So now we have the 3 things that we need. We're going to plug those into the equation. So delta G for this is going to equal negative N and technically this would have a unit moles of electrons. So 2 moles of electrons times Faraday's constant, 96,485 coulombs per mole of electrons, times the cell potential, 1.88 volts. And a volt is the same as a joule per coulomb. Yeah, question?
How did you get the moles again?
I got the moles by looking at how many moles of electrons are being transferred in the equation. You're not going to get it from looking at the numbers here, because when it's balanced, we often have to multiply 1. So this could be 2 or 6, or could be different numbers. It's going to be the smallest common multiple of the ones over here. So that's where the moles of electrons come from. Yeah?
I was going to ask, how did you get positive 2.71?
Good question. So the plus 2.71. So this sodium equation is down here, and it's negative 2.71. But this has sodium ion on the left and sodium metal on the right. This has sodium metal on the left and sodium ion on the right. So it's written backwards, yes? If we write it backwards, we change the sign. Yeah, good question. 1 volt is equal to 1 joule per coulomb. So instead of volt, I'm going to write joule per coulomb so that we can see how the units work out. So the moles of electrons cancel, the coulombs cancel, and we end up with joules. Look here, the book actually gives the answer in joules. So this would be down here 3.63 times 10 to the 5th joules. The answers are the same. Any questions? So we calculated delta G. And the other question, is the reaction spontaneous? Delta G is negative, so it's spontaneous. Any questions? Yes.
I was gonna ask, how did you get the 964,000?
Yeah, so this is a constant called the Faraday's constant. So the F here is the 96,485. And you don't need to try to memorize that number. I keep trying, but I forget. So, yeah, no, you just look it up. That's one of those things, if you use it a lot, you remember. If not, you just look it up. Any other questions? Yeah.
You can add volts and such like the
Pardon me? Pardon me?
You can add volts like the products of reaction.
Yeah, you can add the volts for these two. Just like we would add delta H. Any other questions? Okay, consider this non-spontaneous reaction. Delta G is a positive number. That's what tells us this is non-spontaneous. Based on conceptual reasoning, which of the following best explains why I2 does not oxidize Br minus? So I2 in this reaction would be reduced to I minus. Br minus would be oxidized to Br2. Delta G here tells us that's not going to happen spontaneously, and we're supposed to figure out why. So we've got Br is more electronegative, so we don't expect Br minus to give up an electron. We've got I is more electronegative, so we don't expect I2 to give up an electron. Or Br minus is in solution and I2 is a solid. Solids do not gain electrons from substances in solution. What do you think about choice C? That's just completely bogus. If solids can't gain electrons from substances in solution, how does an electrochemical cell work? You have an electrode that's solid, right? And the electrons go into and out of it. So this just doesn't make any sense at all. Pardon me? Yeah, so for this one, regardless of the reasoning here, we could just say, well, I remember electronegativity trends from Chem 1A, right? Fluorine is the most electronegative, and as they get closer, they get more electronegative. So unfortunately, I don't have a periodic table for me to show you. But is fluorine, chlorine, bromine, iodine in that group 7. Fluorine is the most electronegative. So which is more electronegative, bromine or iodine? Bromine's more electronegative. So this statement is true, that statement is wrong. So even if we knew nothing about the rest of this, you could get it right based on that. So here we've got Br minus. In order for it to become Br2, it has to give electrons to the iodine. Br likes being Br minus, right? And it's already negative. It's going to be harder to get electrons away. It's going to be hard to take an electron away. So the answer is A. Any questions? Okay, so we looked at the relationship between standard cell potential and free energy. Now let's look at standard cell potential and equilibrium constant. So delta G was equal to negative RT natural log of K. We learned that in the previous chapter. We just learned that delta G is equal to negative NF E cell. And so we can set these two things equal to each other. And negative NFE equals negative RT over natural log of K. And then we're going to solve this for E cell. So divide this side by negative NF. Divide that side by negative NF. So the negatives and the N's and the F's cancel out. Over here, the negatives are going to cancel out. So now we have RT over NF times the natural log of K. Well, some of these things are constants, right? R is 8.314. The temperature, this is standard potential, the standard temperature is 298.15. F is Faraday's constant, 96,485 coulombs per mole. And we can change the natural log of K into the base 10 log of K, because the natural log of K is 2.303 times the base 10 log of K. So I do all of that math, and that gets me 0.0592 volts over N times the base 10 log of the equilibrium constant. And you might wonder, well, why did they make it base 10 log instead of natural log? I don't know a specific reason for that, but they did, and that's what everybody does, so that's what we have to do. So this is true at 25 degrees Celsius. You don't need to know how to do that. You don't need to even understand how I did that. This is the equation. I just want to show you it's not made up. Okay, so use the tabulated electrode potentials to calculate K for the oxidation of iron by hydrogen at 25 degrees Celsius. So this is the equation we're going to use. So E cell is 0.0592 volts over N. That's a 9 times the base 10 log of the equilibrium constant. So we need to know what N is, and we need to know what the standard cell potential is. So we're going to get that by looking at this equation in the standard reduction potentials table. So we're going to have to split this into two half reactions. So we're going to have 2 Fe solid is going to 2 Fe 3 plus. And how many electrons would be associated with that? 6. The charge on this side of the arrow is 0. The charge on this side without the electrons is plus 6. So there'll be 6 electrons involved there. And then we've got 6 hydrogen ions. That's going to have some electrons associated with it. Going to 3 H2 gas. This side 0 again. Without electrons, this is plus 6. So we need 6 negative electrons in there. Everybody okay with that? I'm taking the pieces, the reactant and the product that are similar to each other, putting them in one half reaction. And then the other things are going in the other half reaction. I can figure out the number of electrons based on the charges. They're going to end up being the same number because that's what happens when you balance a redox reaction. So what is N?
6.
N is 6 here. Just looking at this, you could probably pick out, oh, I need Fe to Fe3 plus. I'll find that one on here. That's right here. And I need H plus and H2. Oh, that one's right here. They're right next to each other. You could figure that out without pulling these apart. But you have to think carefully to figure out that this is 6. So the best thing is to pull it apart and see how many electrons are involved. Okay, so these are the 2 half reactions. I'm going to write down what their potentials are. So for the hydrogen one, it's 0 volts. And for the iron one, it's negative 0.036 volts. Straight off the chart. One of these has to be backwards because these are all reductions. So one of these is written backwards, and it's the iron. This has Fe3 plus on the left, this has Fe3 plus on the right. So what do we do to its volt? We change the sign. So from negative it becomes positive. Add them together. You see why I like that better? And figuring out which one's happening at the cathode, which one's happening at the anode. And I have to think, okay, an ox and a red cat. Okay, the oxidations is at the anode. Which is the oxidation? The reductions at the cathode. Okay, so I need to take the reduction one and subtract the oxidation one to get my thing. That's just painful to me. It works, and that's how everybody seems to do it, but that's not for me. So there's E cell. So I'm going to plug these in. We're solving for K. So this is kind of messy in terms of algebra. This is not as straightforward as the last one that we did. So if you want to use your solver, you absolutely could do that. So doing it the kind of in your head algebra way, I'm going to get log of K on one side. I'm going to do that by taking 0.036, multiplying by 6, dividing by 0.0592. And then I'm going to do 10 to the x at both sides. So K is equal to 10 to the 3.6486. 4452. And probably 3 safe views. Not 3 sig figs. 2 actually, right? Because this is only 2. Oh, that's right, I can't do that. Yep.
I was gonna ask you, what do you mean
0.0592 is part of this equation. Okay. And so, you know, oh, that's fancy. You know, in a perfect world, you take an exam and you'd be like, oh, I know what equation to use. That's not how it happens most of the time. You get something like this, and it's talking about standard electrode potentials, and it's talking about K. And so then look through the table of useful information until you find a formula that has those 2 things in it, right? And sometimes there's more than one, but usually not. And so that's how you can get the equation. Where did it go? Oh, there it is. Any other questions? Is 4,500 a reasonable value for an equilibrium constant? Sure. They could be negative? No, can't be negative. But they can be super small, like 10 to the minus 30, or they can be super huge, 10 to the plus 30. Okay, so now we can relate all three of these together. So that's a graphic that might be, useful to have on your cell phone. Okay, redox reaction has an equilibrium constant of K equals 1.2 times 10 to the 3. Which statement is true regarding delta G and delta E for this reaction? So we need to think about these relationships. We've got the equilibrium constant, and they're asking us about a sign of E. So we can find the sign of E from this one, right? And we can find the sign of G from that one. We're not going to do any calculation, but we will look at the formulas. So K is a large number. The natural log of this number, is it going to be positive or negative?
Positive.
It's going to be positive. If this is positive, that's positive, this is positive, E cell must be positive. So we can get rid of E cell being negative. If you're not sure if the log of this is positive or negative, take the log of it. And then for delta G, delta G was equal to negative RT natural log of K. R and T are both positive numbers. Natural log of K, positive or negative? Well, if you're not sure, calculate it. It's plus 7. So all of these are positives multiplied by negative. So what's the sign of delta G? Negative. Oops. No. Good grief. This one. Did I do it right this time? E cell's positive, G cell's negative. Any questions? E cell's positive, G cell's negative, K is bigger than 1. Is this a spontaneous reaction?
Yes.
Yeah. Oh, look. See, I put stuff like that in there because it's like, oh, it'd be sure would be convenient to just have those equations. And then I forget and I don't advance it. I should just make it show up. I don't know. Anyway.